Welcome to the NIST Bugs Framework presentation. I am Irina Buzhanova, a computer scientist at NIST and the primary investigator and lead of this project. We are classifying software bugs and weaknesses to allow precise descriptions of vulnerabilities that exploit them. In this presentation, I'll define key notions for BF, discuss the commonly used repositories of software weaknesses and vulnerabilities, and present BF's goals, features, and potential impacts. I'll explain the BF taxonomy, discuss how it's being validated, and showcase it by describing real-world vulnerabilities. We need strict definitions of the software terms bug, weakness, vulnerability, and failure. We define a software bug as a coding or specification error that needs to be fixed. It's the first error in a chain of weaknesses. A weakness is caused by a bug or a previous weakness. A chain of weaknesses ends with a final error, undefined or exploitable system behavior. For example, missing input validation may cause integer overflow and lead to buffer overflow. A weakness type is also a meaningful notion, as different vulnerabilities may have the same type of underlying weaknesses, and we should be able to classify them. We define a vulnerability as an instance of a weakness type that leads to a security failure. It may have more than one underlying weaknesses linked by causality. We define a security failure as a violation of a system security requirement. It is caused by the final error. To communicate precisely about software security vulnerabilities, we need a taxonomy for describing their underlying bugs and weaknesses, and the eventual security failures. And this is what the bugs framework is about. Let's, for example, look at beta log, a pattern observed by CISA and reported in its Industrial Control Systems Advisory, which lists 25 similar vulnerabilities found in multiple real-time operating systems. Using the bugs framework classification, we describe beta log as follows. Due to improper data verification, DVR, an attacker can craft an input to a type computation, TCM, that creates an integer overflow wraparound, leading to allocation or reallocation weakness of an undersized buffer, MAU. Therefore, a memory addressing weakness allows a pointer to be moved over bounds, MET, leading to a memory use weakness or a memory write weakness, resulting in a buffer overflow error, MUS, eventually leading to a failure, such as denial of service, or even worse, remote code execution. There are several commonly used repositories of software weaknesses and vulnerabilities. We focus on the following. CWE is a community-developed list of software and hardware weaknesses types. CVE is a catalog of publicly disclosed cybersecurity vulnerabilities. CEF is an organization of publicly exploited CVEs with top priority for remediation. They are not necessarily the most severe, as many of those don't get exploited in the wild. NVD is the US government repository that links all CVEs to CWEs and assigns CVE severity scores. It also links its entries to CEF. CWE and CVE are widely used, but they have some problems. Many CWEs and CVEs have imprecise descriptions and unclear causality. CWE also has gaps and overlaps in coverage. Additionally, there is no strict methodology for tracking vulnerabilities weaknesses, nor tools to aid users in creation of vulnerabilities descriptions. This is an example of an imprecise CWE definition. It states, the application deserializes untrusted data without sufficiently verifying that the resulting data will be valid. It's not clear here what sufficiently means, and verifying that data is valid is also confusing. It should say, without validating and verifying it. Unclear causality in CVEs leads to wrong CWE assignments. For example, in this CV, lack of input validation leads to integer overflow and then to buffer overflow. NVD labels it with CWE190, integer overflow or wraparound, while the cause is CWE20, improper input validation. The full chain is CWE20, CWE190, CWE119, the last one being improper restriction of operations within the bounds of a memory buffer. In addition, note that if chains are incomplete, there is no way to backtrack them and reveal the bug from a vulnerability description. Being an enumeration, the CW also has gaps and overlaps in coverage, which leads to confusion. As an example, if we arrange buffer overflow CWEs by read or write over or under the bounds, on the stack or heap, the gaps and overlaps can be easily spotted.